All right. Good evening, everybody. Once again. So, what were we doing? Yeah, we were demand paging. Yeah, this is process and resource, and we were doing some resource allocation graph with deadlocks. We are actually trying to solve everything out. Okay. Right. So it deleted it, and let's do this. So let's do the resource allocation graph. P1, P2, P3, P4, R1, R2, R3, R4. So R1, the resource is allocated to P1, and resource 2 is allocated. Alright. And now what? P1 R2, P1 is requesting this one, P2 is requesting this one, P3 is requesting this one, and P4 is requesting this one. So aborting P1 will make the system deadlock free. Let's abort P1. That means we remove this. So this will be removed. Right. So maybe P or P3 is requesting for R1 and it get fulfilled. And are we having a deadlock? One. Okay. So 1, 2, 3. Uh, did we do that one wrong? R1, P3, R2, P2, P2, R3, P2 to R4. Where is P2 to R4? We did not draw every edge. We messed up that one. P1, P2, P3, P4, R1, R2, R3, R4. So R1 to P1, R2 to P2, R3 to P3, R4 to P4. Nice. And P1 to R2, P2 to R3, P3 to R1, P4 to R2. Okay, we missed this edge, and if you delete P1, the resource is to P1, so this edge will be deleted. And now something is requesting. What is requesting? P3 is requesting R1. P3 is requesting R1. So this gets, kind of fulfilled. So this got fulfilled. And after fulfillment, what do we have? So are we having a deadlock? So obviously this one will be removed, and 1, 2, 3, maybe 1, 2. No, what's wrong? Should we include that edge or what? R2, P2, R4. P2 to R3 and R4. P4 to R2, yeah. P2 to. Why am I messing this up? P2 to R3. P3 to R1, yes, this one. P2. Okay, there are 5 things, man. P2 to R4. I have been keeping on missing this edge for some reason. I don't know, it might be my overlook. P2 to R4, yes, sir. So 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. So deadlock. So let's come to initial stage now, and so R1 to P1 and P1 to R2. And now, alright, 1, 2, 3, 4, 5, 6, 7, and 8. Wait, what? 1, 2, 3, 4, 5, 6, 7, and 8. But you need to have 9. Okay, 1, 2, 3, and 4. And P1 to R2. P2 to R3, yeah. P3 to R1, yes sir, this one also. And now let's about P3. If you about P3, P3 is requesting for R1, so this will be removed, and this will be removed as well. So now R1 is allocated to P1. Are we still in a state of deadlock? Okay. Need to solve this one. Okay, there is no cycle over here. P1 needs R2, yeah, which hold P2. P2 needs R3 and R4. R3 is 4, but R4 is held by P4. P4 needs R2. P2. No, how did I get the cycle? So cycle is just not enough. Like not a sufficient condition. Create analog detection and prevention using Banker's algorithm. Yeah. Yeah. This guy is an idiot. So it could not even do the basic Banker's algorithm. So we aborted P3. P1 needs R2, which is held by P2. P2 needs R3 and R4, out of which R3 is free. But R4 is held by P4 and P4 needs R2, which is held by P2. Okay. 1, 2, 3, 4. Wow. How did I miss this one? Because I was not drawing correctly. That's the problem. You could have just told the recycle dude. Oh my god. You know what? P1 to R2, P2 to R3, P3 to R1, P2 to R4, P4 to R2. Aborting P2. Let's say we abort P2. So this resource is being held by that. This gets removed, and P2 is requesting R3 and R4. These get removed as well. Nice. So now you just need to check for deadlock 1, 2, nothing, and resource 2. There is no incoming edges, P3 and P4. If you check for every resource, that is sufficient. Yeah. So now let's let's remove P1 and P4. So resource 1, 1, 2, okay, and 1, 3. Nice, right? P4 to R2. So now what if you remove P1? Now how can you detect cycle with this algorithm? 1, 2, 3, 4. But I started from here. 1, 2, 3, 4. That's not a cycle. 1, 2, 3, 4. That's a cycle. Okay, got it. And now what if you remove this one, P2? I mean P3, sorry. 1, 2. Are we still in the cycle? 1, 2, 3, nothing. So there are nothing else to check. 1, 2, nothing else. 1, 2, 3, 4. That is a goddamn cycle. See? This is a cycle. So pink cycle needs to be removed. That's it, man. 18 minutes of analysis for just this question, and we'll be cooked. A demand paging memory management system with 32-bit logical address and 20-bit physical address. A page size of 248 bits, assuming that the memory is byte addressable. What is the maximum number of entries in the page table? So 32-bit and page size. So offset is 2 power 10 is 1024. 11 bits, and physical address is 20 bits. Page size, entries of a page table. So page will be 32 minus 11, how much? That is 21. Page table is 21 bytes, and page size is logical address is 28 bits. Page size, okay. Number of entries, right? Total number of possible entries by, okay, 2 power 21. Okay, that is what we did. Okay, this is 2025 set 1. In a multi-programming environment, the following C program segment is executed. The process goes to an IO queue whenever IO-related operation is performed. Assume that there will always be a context switch whenever a process requests for an IO. Also, whenever a process returns from an IO, the process will enter to ready queue during its lifetime. Is so scanf IO operation once it is 20 iterations, 20 printf statements, 20, so total 21 IO operations. Yeah, we were not asked to know. Yes, exactly. We were not asked the number of context switches. All right. So computer has two processors, M1 and M2, four processors, CPU burst times. Okay, and these are the only processes. Non-preemptive priority scheduling with priority decides as follows. So M1 priority, P1, P3, P2, P4. Okay, M2, P2, P3, P4, P1. If PI is scheduled to a processor MK, if PI is scheduled to a processor MK, if the processor is free and no other process, PJ is waiting with higher priority. So CPU burst times are given. So M1 will initially have process 1 and M2 will initially have process 2. Um, right. So 20 milliseconds and 16 milliseconds. So they are at average waiting time for P1 is 0 and P2 is what? Is 0 as well. So after 16 seconds, P2 will be completed and it can take P3. It just takes P3 at 16th instance. And non-preemptive scheduling. So this one cannot go to this one. Alright, so it is locked in here. And what is the best time for P3? So P3 has 25 seconds of burst time and P3 has a waiting time of 16. And so now what do we have? P4. So P1 after 20 seconds it is completed here and P3 is already M2'd. So no. P2 P2 done, and P4 will be executed after 20 seconds. And what is the burst time? 10 milliseconds, and the wait time is 20. So 36 by 4, it is 9 milliseconds. Exactly, this is what I have done. Wow, we at least remembered it. So we have scheduling mainly, and we have pacing, and we have deadlock detection, and avoidance as of now. Internal fragmentation 502 megabytes, million bytes, okay, megabyte, 64 kilobytes file. Okay, you can calculate the number of blocks from this one as well. A linked allocation, then in linked allocation each data block reserves 4 bytes to store the pointer to the next data block. The link part of the last data block and its null pointer also 4 bytes. Suppose a file of 1 M bytes needs to be stored. Okay, 2 power 10, 2 power 20. The spaces in bytes that will be the amount of space in bytes that will be wasted due to internal fragmentation is. So block size, block I can kind of visualize that one, 64 kilobytes, and disk size is 512 million bytes, so that is 64 into 2 power 10, that is 512 into 2 power 20. A block reserves 4 bytes. Alright, block reserves 4 bytes. 1 M needs to be stored. So 1 into 2 power 20 needs to be stored. Actual size is 64 into 2 power 10 minus 4. 1024 into 64. Let's open our gate calculator. So 64 times 1024, 65536, and minus 4, 65532 can be stored in one block. And what is 2 power 20? 2 power 20, that is 1048,576 divided by 65532. You will get 16.009. Alright, so 16 full blocks plus something. You need to find the value of something. So 65532 times 16, 1048,512. Full blocks. So 1048,576 minus 1048,512, that is 64 for extra, and internal fragmentation is 65532 minus 64, 65532 minus 64. 4 6 5 4 6 8 6 5 4 6 8. We are not wrong. 6 5 4 6 8. Yep, this is what we did, and we did it well. We also did this one, if I'm not wrong. I feel like that is enough of OS. What do you guys say? We did. We did some discrete mathematics. We did some digital logic. We did some programming and AS. We did some algorithms. We did some theory of computation and compiler design. Within 1 week, I will start doing compiler design as well. We can do everything here. Literally, we can do everything over here. So we will start DBMS. It is closed for some reason. Duplicate. Uh-huh. Okay. Why is it flagged? No, what is wrong with all of this? My god. Okay, 2025. This is the transaction. Oh god. So this is a transaction T1 and T2 with that items X and Y. Conflict serializability. We did that one. There are like few rules for conflict serializability. So they can be serializable, like the order can be changed without causing a conflict. That is what conflict serializability actually translates to. So if you read something, I mean, if you wrote something, all right, how do I put this? R1X and W1Y. So there is something called dirty, dirty read or dirty write. Dirty read. Yeah, dirty read. Dirty write. Okay, it's dirty read, yeah. Wait. A transaction reads the data that has been modified by another transaction but not yet committed. A transaction reads uncommitted data. Reading uncommitted data from other transaction. The article was recently updated, and so let's see. We are reading X, okay, and we wrote to Y, so there should not be R to X here. Yeah, there is no R to X. And you wrote to Y, there should not be W1y after, okay. Which of these? All right. So let's see. You wrote x and all right. So R1 should not read x. R1 should not read x. So it read x before committing. So it is not conflict serializable. So you wrote x and you should not read x. Okay, R1x. So you wrote y and R2y should not be there. R2y is not there. This is conflict serializable and you wrote x and there should not be R1y. There should not be R1y. Oh wait, you need to check everything, right? R1x and there should not be W2x, okay? You wrote 2y and there should not be R2x. There should not be R2x. Yeah, there is no R2x. And you wrote 2x and there should not be R1y. Yep, there is no R1y and R1y should not be there. R1y, no. W1x, okay. So you wrote 2x and there should not be the transaction 1 should not read x, so R1x. There is R1x here. So C is conflict serializable. B. What do you mean by B? R1x. Okay, let's see. Did I check that wrong? Let's see this guy. Okay. I wrote, I read. Precedence graph. Uh-huh. So we can do something like this. Since they are for two transactions only. R1 to W2. 1 to 2 there is 2 to 1. W2x and W, alright, R1x. Yeah. Okay, so okay, that's not it. snip was removed. Oh my god. So 2x to 1x and 1x to 2y to 1y. Okay. So is it also a cycle? Yeah. So 1x to 2x and 1y to 2y. But the answer was told as B. No, what is this guy doing? अरे क्या कर रहा है भैया? Okay. W2x. We wrote W2x and there is no. Now let's draw this man. So W2 x and x operating, y and y operating. That's it, right? It is not operating on that. That is as simple as that. For R of x, R1 of x, W2 of x, W1 of y, W2 of y, R1 of x, W1 of x, C and C. So, alright, same data, W2x. Okay, that is a problem. That is a problem. Got it. So you just need to put pen and paper. Wait, it is. Alright. Which of the following is our correct as queries to return names of students enrolled in course number? So this is students table, roll number, name, age, CGPA. This is student table. So we got course table, C number, C name, credits, and enrolled, roll number, C number, and grade. These are the primary keys. So select, alright, names of students who enrolled in course number 1470. So names of students, uniquely identification, enrolled in course number 14, alright, from select name from student where exists, alright, select from enrolled E where E dot course number is equals to 1470 and E dot roll number is equal to S dot roll number. That makes sense. Select S from S dot name where student from student S where size of okay. Select everything from enrolled E where E dot course number is 1470 and E dot roll number is equals to S dot roll number. Okay, size of is a function where 0 is less than natural join enrolled. So you are joining students and roll number. Yeah, everything is logically correct. So size of is not part standard SQL. Okay, let's ask GPT. It should know better. How am I supposed to know size of is not part of standard? You know, count is a way to check row existence, okay? Mm, we also did this one where each node can hold at most 4 keys. Route to leaf path consists of the following nodes. Okay. A route to leaf 20, 22, 25, 26. Data entries is a leaf, okay? The pointer between K1 and K2 points to a subtree containing keys in K1 and K2. And when a leaf is created, the smallest key in it is copied upon its parent. A record with key value 23 is inserted. So 23 is inserted. in the parent of the leaf, the smallest key value in the parent of the leaf that containing 25 is the smallest key value in the parent of the leaf that containing 25. 25's parent. So it causes an overflow, obviously, and it will be split. How do you split it? Do you split it into two parts? Yeah, precisely. It is actually this. And precisely, so it is between 19 and 33. So this is this. So the middlemost value is 23. It will be pushed here. And the elements that are smaller than 23 will belong to this, that is standard B tree overflow case. And again it will be overflowed, so 23 will be sent here. So now it will be 23, 49, 79 and 83, and the values that are smaller than 23 are 7 and 90, and the values that are greater 33 and 44. So 20 and 22. Yep, they are larger. And that 25 and 26 are smaller. So 33 is the parent. 33. Okay. Present inserting 23 violates. Okay. Again violated. Okay. 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 Yeah, so 23 will not be moved. That's the only difference. Yes, that is enough on this side. The side's not loading out. Two joint holders of account A attempted simultaneous transfers of 10,000 from account A to account B. Both transactions are at the same value. Rupees 11,000 was the initial balance of the initial in A, and we are allowed to go through. B was credited to 10,000 twice, so ended up with a value of 1,000. What is the following properties? Okay, this is nice. Acid properties. A basic question of acid properties. So this is account A and this is account B, and it got 11,000 rupees. Both transactions are at the same value. So after 10,000, so what I was trying to say is B was credited 10,000 twice. Okay. Isolation was not validated because from joint holder person one point of view and person two point of view, they feel like they are accessing just them. So atomicity is like a process should either complete or not complete. But after 10,000 got credited and the remaining the 10,000 should be subtracted. So that is not completely done. And consistency, atomicity and consistency, if I'm not wrong. Okay. Ensures all properties of a transaction are completed or none are. We are correct with that one. Each transfer individually must complete. Right. That's what I'm Where did your 20,000 come from? Okay, 20,000 like total too. Your 20,000 was debited. Concurrent transactions should not interfere with each other. All right. So that needs a basic understanding. Partial failure. Debited A, credited B. radii and David radii. Okay. Transfer 10 rupees, okay. Got it. So I had a wrong understanding about the acid properties. So the conclusion is atomicity, debit, credit happened, and durability, no crashes. So atomicity and durability. So about consistency, one valid to another valid. Printing, alright, showing more currency. And isolation, feeling of one one transaction at a time, but be credited by 20k when it should 10k. All right, that makes sense. Functional dependencies were given. So A, B, C, D, E, that's relation 1. D to E, EA to C, and A, B, C, D, D to E, EA to B, EB to C, A to D, A to B, C to A. So we need to, 1NF is very simple. So we need to look for, okay, let's recall the rules of 1NF, 2NF and 3NF. 1, 2, 5, NF. Study tonight. Okay, he cooked something here. First normal form. Single atomic valid attributes and columns, okay. 2NF partial dependency. When a table has a primary key, all columns not included should depend. You cannot part of it. Student ID. Transitive dependency. In a table, we have some column that acts as a primary key and other column depend on this column. But what if a column that is not a primary key depend on another column that is also not a primary key? Then we have a transitive dependency. Okay. Candidate number, candidate name, candidate number, state, candidate country. X is a super key or Y is a prime attribute. Okay. Candidate number to candidate state to candidate country means candidate country is transitively dependent on candidate number. So D से ये आएगा E A से भी आएगा से B E है to B. Both are in 3NF. Okay. I messed up. Yeah, X is a super key and Y is a prime attribute. And D. C is a candidate key. So D is needed for E, and if I provided with another information, let's say okay D, okay, so with D, alright, let's get some closures. D, and what can you get with D? You cannot get anything with D. With A you cannot get anything, with B you cannot get anything. Suppose let's say if I give DB, with D you can get E, and with EB, you can get C, and you cannot get A by any ways. Oh wait, yeah, we have seen that. If it cannot be derived by anything else, it should be part of candidate key. AD is a candidate key. Yeah, I have heard and closures and private attributes. Okay. So you have ABC will be a candidate key. I mean C will be a key because it is needed. For a relation to be into NF, all non-prime attributes should be fully independent of the primary key. So is D2E partial dependency? Let's ask it. Is D2E partial dependency? Alright. It is hallucinating.